Hello, and welcome to a video on Edexcel A-Level Chemistry. This one is about halogenoalkanes, which is part of Topic 6, and I'll be covering the specification points of 30 to 36. So, first and foremost, what is a halogenoalkane? So, a halogenoalkane is an alkane, except it has a functional group which happens to be a halogen atom. The halogen atom that you could expect to see could be something like fluorine, chlorine, bromine, or iodine. Essentially anything from the halogen group, group 7. The prefix when you name a halogenoalkane depends on what the halogen actually is. So for example, you have fluoro, because the carbon is bonded to a fluorine atom here, chloro, because you have a carbon bonded to the chlorine, and then bromomethane, because this carbon here is bonded to this bromine atom. And finally, iodopropane, because you have iodine bonded to this carbon. However, there is another way in which we can classify halogenoalkanes, and we can do that by calling them a primary, secondary, or tertiary halogenoalkane. To do that, we look at the halogen atom in the compound and look at the carbon atom to which it is bonded. So for example, if we look at the primary halogenoalkane over here, we look at this carbon to bromine bond. So you see the bromine is bonded to this carbon over here, and this carbon is only bonded to one other carbon. That makes it a primary halogenoalkane. If we look at the secondary one over here, once again we look at the carbon, which the bromine is bonded to. However, that is bonded to both this and this carbon. Because it's bonded to two other carbon atoms, that makes it a secondary halogenoalkane. And finally, with the tertiary one, you look at the carbon atom that the bromine is bonded to, and that is bonded to 1, 2, and 3 different carbon atoms, and that makes it a tertiary halogenoalkane. So this system is quite simple, and you will come across it a lot in questions, so you should be well aware of this. And now that we've covered how to classify halogenoalkanes, we can move right on to looking at their reactions. Halogenoalkanes can react with ethanolic potassium hydroxide to produce alkenes in this elimination reaction. The conditions required for this will be that the halogenoalkane has to react with a warm alkali dissolved in ethanol, and that the mixture must be heated under reflux in order to prevent the loss of volatile reactants. Here's an example of this elimination reaction on the board, which will produce a alkene along with water and potassium bromide. In order to understand the rest of the reactions we're covering, you'll need to know what a nucleophile is. A nucleophile is a species that donates lone pairs of electrons to electron-deficient regions. Here are three important nucleophiles that you need to be aware of: water, cyanide ions, and hydroxide ions. I've highlighted the lone pairs on them, just in case you need to see them. Now, we need to learn about the nucleophilic substitution mechanism. The reaction we're going to use to demonstrate this is the reaction of a halogenoalkane with aqueous potassium hydroxide. The fact that it is aqueous is very important. So firstly, we want to draw out the displayed formula of our halogenoalkane, along with our hydroxide ion. Make sure to include the charge and the lone pair on the hydroxide ion. Now first, we need to draw a curly arrow from the lone pair over to our carbon atom to show that the lone pair is being donated to the carbon atom. We also need to demonstrate the fact that our carbon to bromine bond is polar. We do this by drawing a delta negative symbol here and a delta positive symbol here. And now this bond over here is going to break in a heterolytic fashion, meaning both of the electrons from this bond will go over to the bromine. We can demonstrate that by showing an arrow going from here over to the bromine atom. After that, we can move on to our second step, which is also the final step in this case. And over here, if I just draw it out, you can see that our hydroxide ion has bonded over to the carbon over here. You also need to remember to draw out your leftover negative bromine ion. And that concludes this reaction right here. Unfortunately, the previous example is not the only nucleophilic substitution you need to be aware of. You also need to know what happens if a halogenoalkane reacts with warm excess ethanolic ammonia. By warm, I mean you have to warm the solution together. So the start of it is the same as with the previous mechanism. However, you'll notice that the nitrogen atom here has a positive charge. This means that the reaction is going to continue. So what will happen here is that this nitrogen to hydrogen bond is going to break, like that, going towards the nitrogen atom. And the lone pair from the nitrogen of another ammonia molecule is going to be donated to this hydrogen. And after that, you'll get an amine produced, as well as a positive ammonium ion. Another example of nucleophilic substitution that you're going to need to know about is what happens when you react a halogenoalkane with a cyanide-containing compound, such as potassium cyanide. Now, this is very similar to what you've seen in previous examples, except your nucleophile will be the cyanide ion here, and the lone pair that you're going to need to worry about is on the carbon atom. So, as per usual, you need to indicate this is a polar bond between the carbon and the iodine, so you put delta negative on the iodine, delta positive on the carbon. Then you want to show that the carbon to iodine bond is breaking, with the electrons going to the iodine. So once again, your curly arrow to the iodine, and then you want to show the lone pair from the cyanide ion being donated to the carbon, so yet another curly arrow over here to the carbon. And as your products, you'll get a nitrile compound here, and don't forget your leftover iodine ion. Now, one thing you should take note of is why this reaction could be deemed as useful. And that would be because it actually increases the length of the carbon chain. As you can see here, with iodoethane on the left, there are 2 carbon atoms in the chain. However, cyanide actually has a carbon atom in it. So over here, in your nitrile, you actually have 3 carbon atoms in the chain, therefore lengthening it. This will be very useful in case you get an exam question which asks something about why this reaction is useful. The last important reaction you need to be aware of in regards to the halogenoalkanes topic is what happens when you react a halogenoalkane with water. This is known as the hydrolysis of a halogenoalkane, and this is really important for a number of qualitative experiments. What happens is, when you react your halogenoalkane with water, you'll get an alcohol and your halogen ion. However, if you add silver nitrate to this, a halide precipitate can form, because with the original hydrolysis reaction, you get left over with a halide ion. This will actually react with the silver nitrate and form a solid precipitate of silver or bromide, fluoride, chloride, or iodide, depending on what the halide is. This is important for many experiments that I'll describe very shortly. Now, an important experiment that you need to know about is how to figure out the rate of hydrolysis of a halogenoalkane. You can do this, and will want to do this, if you want to figure out the trend in the rate of hydrolysis depending on the halogen, or depending on whether it is a primary, secondary, or tertiary halogenoalkane. So the way you would do this is have one test tube for each of the halogenoalkanes that you're testing. Add your halogenoalkane to that, as well as ethanol and silver nitrate. The reason you're adding ethanol is to act as a solvent. And then after you add the silver nitrate to the solution, you need to time how long it takes for a precipitate to form in each of the test tubes. The halogenoalkane with the fastest forming precipitate has the fastest rate of hydrolysis. And if you want to use this to test which halogenoalkane is in your solution, you look at the color of the precipitate. If you test a chlorohalogenoalkane, you would get a silver chloride precipitate, which is white. A bromoalkane would give you a cream precipitate, whereas an iodoalkane would give you a yellow precipitate. You will also want to know about the trends in the rates of hydrolysis of halogenoalkanes. Firstly, if we look at primary, secondary and tertiary halogenoalkanes, primary halogenoalkanes will have the slowest rate of hydrolysis, whereas tertiary halogenoalkanes will have the fastest rate of hydrolysis, with secondary ones being somewhere in between. This is because tertiary halogenoalkanes are more reactive. You don't need to know why they're more reactive, but simply that the trend exists, so you should be aware of it. However, if you look at the halogen involved in the halogenoalkane, you can see a clear trend in their reactivity, where fluoroalkanes will have the lowest rate of hydrolysis, and iodoalkanes will have the fastest rate of hydrolysis. This is a clear trend in that the rate of hydrolysis increases as you go down the halogen group. You do need to know the reason for this trend, and that's because the bond enthalpy decreases down the group, increasing reactivity and making the carbon to halogen bond easier to break. This is because the bond enthalpy will decrease down the group, as the halogen atom will increase in size down the group. The increase in size means that the bond will be weaker, so it's easier to break, hence a lower bond enthalpy. If you're doing an experiment to look at these trends, you need to make sure that you isolate the certain bit of structure as the reason for the trend. For example, if you're testing whether a chloroalkane has a higher rate of hydrolysis compared to a fluoroalkane, you need to make sure that they have the same carbon skeleton, because if one is secondary and one is tertiary, for example, that would also affect the rate and give you an unfair experiment and an incorrect result. And if you're testing whether a tertiary halogenoalkane has a faster rate of hydrolysis than a primary halogenoalkane, you need to make sure that they have the same halogen group bonded to them. That concludes the halogenoalkane part of topic 6. Thanks a lot for watching, and please leave any feedback or questions if you can.